Training a neural network is the process of adjusting the learnable parameters of the network. In the beginning, all learnable parts of a neural network are random. Then the training starts by feeding the network a set of input data and the corresponding output data. The network then makes predictions based on the input data and compares them to the expected output data. The next step is to calculate the difference or error between the network's prediction and the actual output. This calculation is usually done with a classic known in numerical weather and climate prediction, namely the L2 norm or the root mean squared error. Still, other choices are available depending on the problem we are trying to solve. The error is then used to adjust the parameters of the network in a process called backpropagation. This process is repeated multiple times using different sets of input and output data until the network is able to accurately perform the task. This process is called stochastic gradient descent, trying to find the lowest error possible a network can produce. We often can't fit the entire training data into the memory of our PC. That's why we split our training data into batches that we feed into the network iteratively. This can be an essential value to adjust, since a larger batch size can stabilize the training process. Imagine the extreme where we feed a single data point per training pass, a batch size of 1. Then a single outlier in our data can adjust the network in a completely different direction due to high error compared to the optimal neural network configuration. When the network has seen the entire dataset, we call this an epoch. The batch size is the first hyperparameter we got to know that you can tune to improve model training. We call this a hyperparameter because they are values that govern the training of the actual learnable parameters in the network. The next hyperparameter, called learning rate, determines how much the network parameters are adjusted during the training process. Considering that we use only subsets of the entire training data for each step, we don't want a single batch to modify the network as if it was the whole dataset. We can think of this as adjusting the step size we take with every error calculation. A higher learning rate can make the training faster by taking larger steps towards a minimum. Still, it can also entirely miss a minimum. A lower learning rate makes the training process slower, but it can also make the network more accurate. That's why we often put the learning rate on a schedule, where early training epochs have high learning rates. We decrease the learning rate as epochs increase, following a cosine shape. There are many other hyperparameters that can be roughly divided into categories of architecture, optimization, and regularization. Examples of hyperparameters in architecture include the number of layers or their width. Optimization contains the batch size and learning rate we just discussed. And regularization includes different ways to avoid overfitting the network, like assigning a probability to randomly switch off learnable parameters per training step, called dropout. Hyperparameter tuning is the process of adjusting these values to find the best combination for a specific task. This process can be automated and is time-consuming. Important note, this needs special care to not overfit the network to the data, which is a network memorizing the data instead of understanding the underlying relationship. Nevertheless, it can help to ensure that a neural network can predict at the highest possible performance.